Hello Year 12, this is a lesson on exercise 1D, modulus argument form. So as the title says, we need to talk about the two words modulus and argument. So here are the definitions. The modulus of a complex number is the distance from the origin to its point. And the argument of a complex number is the angle that it travels in the anti-clockwise direction from the positive real axis. So if you look at the diagram, it's pretty self-explanatory, but if this is the complex number that we have represented on an Argand diagram, then the length of this line pretty much would be the modulus, and this angle over here, the theta, would be our argument because it is how much this point travels from the positive real axis anti-clockwise. Hope that's clear enough. Now, in terms of the notation, modulus of z, we would write it as mod z for short, or we could write absolute value of z. And if we ever try to find the actual length, the modulus, then we just apply the Pythagoras' theorem. We know the horizontal displacement would be x, the vertical would be y, so the modulus would be square root of x squared plus y squared. And we often use the letter r to represent it because if the point moves around according to different values of theta, then it will start to rotate. So the larger the theta, obviously the more to the left it will travel, and it goes wheeong, and it usually makes a circle if it keeps rotating. So then this length could often be referred to as the radius of that circle. So we like to call them r. Just note that if you have the modulus of z squared, then it's the same as the multiplication of that complex number by its conjugate, because we know that z times z bar would equal the sum of the squares. So if we square the modulus, we will just get that product. Now with the argument of z, we say arg z, like this. And you just have to realize that the x-coordinate can be represented by r cos theta and y as r sine theta. I'm pretty sure you guys have already seen this before when you were first defining polar coordinates. You probably didn't you might not have heard the name, but you would have first seen it in trigonometry in year 9/10 when you were doing points on a unit circle. So if you remember that, that's great. If you don't remember that, that's also fine. Now, using the definitions above, we can express any complex number in the form of this, and that is because for any complex number z, we have x plus iy. We can replace the x-coordinate with r cos theta, replace the y-coordinate with r sine theta, and just factor out the r, and we get this expression. But as abbreviated form, we can write it as r cis theta as well. Cis because c for cos, and then is for I sine. It's literally like the initials. And notice how the theta is the same theta, so we can just combine it into one notation. You should know how to go back and forth. Now, since it requires knowing the modulus of that complex number and the argument of that complex number, we call it the modulus-argument form, but in short, we just call it mod-arg form. Or, as I said before, it involves the polar coordinates, so we also call it the polar form, but I think mod-arg form is the more popular terminology. Now we are going to define the angle that it travels to be the principal argument, so that the angle goes between negative pi to pi. So the actual size of the angle won't exceed 180 degrees. So just a bit of difference. So the mod-arg form that we just learned has a different name, polar form as well. and it requires us to find the distance and the angle, whereas the ones that we have been using so far will be called the real imaginary form, or you can label them as Cartesian form because it requires us to have the x and y coordinates of that point. Let's get to the first example. So it says express each complex number in real imaginary form. We just got to expand it out and evaluate it one by one. So if it says 4 cis pi, I can just expand that as 4 bracket cos pi plus I sine pi. And those are just, we can find the exact values of them. Cos pi would be -1, so I get 4 times -1, which is -4. And then sine pi is 0, so the imaginary part is gone. For the second one, 2 bracket cos pi on 6 plus I sine pi on 6. And again, we just keep evaluating. And then expand and simplify where we can. Same with this one. Now we don't have anything at the front, meaning it's just 1. That's useful. Just make sure you get the signs right for these arguments. So for cos 2 pi on 3, it's going to be -12. But for sine, it's going to be positive √3 on 2. Oh, good. That's pretty much it, guys. Example 2. If we have to express the Cartesian coordinates to the mod-arg form, then it's important that we sort of visualize how it looks like. So for this one, if z is equal to 5i, we can pretty much see that it's going to be a vertical line, and the point just passes 5 on the imaginary line. So if I think about that as a line that started from the positive real axis and has moved, then I can see that it's moved by an angle of pi on 2, anti-clockwise of course. And if I consider the circle, my radius r would be 5, or the length of that interval would be 5. So I can say that this in mod-arg form would be 5 cis pi on 2. Similarly, I'm going to picture this one as well. If it's 3 minus 3i, it's going to be stretching this way, 3 this way, -3. So it looks like the modulus of that excuse me, modulus of that interval would be just the use of Pythagoras' theorem. It would be, I'll just quickly draw it down there. So that's √18, which is meant to be 3√2. Or you can actually use the ratio of isosceles triangles. So whatever this length is, you just have to multiply by √2. And the angle that it travels, again, it's an isosceles triangle, so we know that it's traveled pi on 4, but it's going clockwise, so the argument must be -pi on 4. So the answer would be 3√2 cis -pi on 4. And because of the negative sign, I just put in brackets. Last one, -4 minus 3i would be around there, -4 minus 3. So I guess in order to find the principal argument there, I would have to use trigonometry to find this angle first. Let's give it a name, alpha. So as a side working, I think alpha would be tan inverse of 3/4. And if the question tells you how to round it off, follow the question. If it doesn't say, you can choose, I usually go with 2dp. So if we round it off to 2dp, I get 0.64 in radians. So then the principal argument would be negative pi plus whatever alpha is. So if I jot that on the calculator, I get negative 2.50. Maybe I should do approximately equals to sign there as well. With the modulus, it's 4 versus 3. We can see that it's 5 straight away, so it's going to be 5 cis negative 2.50 2dp. I hope that was pretty straightforward. Now let's go back to the syllabus dot points. If you look at the part of complex numbers part 1, there's this whole list of dot points, but the syllabus does require you to prove and use these identities. So some of it we've already had a look. For example, these ones are very easy to prove. That one I've already noted at the beginning of this video. But what I want you to try and do is to pause the video and prove the first 4 dot points. So it's those 4. They're fairly easy to prove, I think, hence why I named it Mission Possible. But feel free to work collaboratively. You can work on your whiteboards or whatever you'd like. And if you get stuck, you can search it up, but I think with your brains, it should be fine. Or you can ask me. Maybe I'll put up the solutions later on. Now, 2 more things to have a look at. First of all, we need to always link it back to geometrical representations. So when we think about rotating the complex number interval or enlarging them, we often look at the multiplication of those 2 complex numbers. So if we multiply 2 complex numbers z and w, then we have the modulus of zw being the multiplication of mod z and mod w. And with the angles, if I look at the argument of z times w, then I end up looking at the sum of angle for z and the angle for w. It's fairly easy to look at that on the diagram. Maybe you can try this, try sketching it by yourself and see what I mean by that. And to understand these 2 dot points geometrically, that just means that if I multiply z by w, then z would be rotated anti-clockwise by the argument of w because I'm adding on that angle, which means I am rotating by that angle anti-clockwise. And with the modulus, z is basically being enlarged by however big or small the length of w is. We use the term enlarged, but really it could be like decreased in size. We just generally say it's enlarged. So let's use that to try some of the examples straight from Cambridge. Example 23 in the textbook. Now let z equals to 1 plus I. Find in Cartesian form the complex number w such that the multiplication ends up being a rotation of z by pi on 3 about the origin. So as I said, it will be rotated by the angle of w. So that means I want my angle for w to be pi on 3. So the complex number w would be cis pi on 3. Oop, that looks ugly. Pi on 3. Now the modulus of w, it doesn't say it's been enlarged, so it must stay as 1. So I'm just going to write cis pi on 3. Oh, it says in Cartesian form. So I'm going to have to expand this out as cos pi 3, pi over 3, plus I sine pi over 3, which is going to be half plus half, plus I root 3 on 2. I think that's good enough. B, evaluate WZ in Cartesian form. Oh, there's going to be a bit of multiplication to do. So WZ, literally the coordinates for W multiplied by the coordinates of Z, double rainbow, I times I, so it's negative root 3 on 2. And then I might just collect the real parts and the imaginary parts together because it always looks nicer that way. And because everything's over 2, I might factor out the half as well. So it would become half of 1 minus root 3, that's the real part. And we've got 1 plus root 3i for the imaginary part. Yep, I think that's simple enough. And then lastly, part C says, verify that mod WZ is equal to mod Z. And then plot Z and WZ on an eigendiagram. We just got to show them manually. So let's try and find mod Z. That would just be the formula that we talked about before, root x squared plus y squared. We get root 2. Easy. And then for the modulus of WZ, we could do the Pythag theorem on this one, but as you can see, it's pretty complex. So we're going to try and find a shortcut. So why don't we look at the square of the mod? Because then what we end up getting is we get a quarter, of course. We get half squared at the front. And then inside, we end up doing x squared plus, plus y squared. I was meant to say y, but I wrote down y. So we get the sum of the squares of the coordinates, basically. And the benefit of that is that some of the terms will cancel out. So the only terms that are left in this expansion would be 2 lots of the 1 squared, which is 1, plus 2 lots of the root 3 squared, which is 3. I hope everyone is able to do that calculation pretty quick. So I get a 2, which means if I square root to get the actual modulus, it should be root 2. Therefore, we have proven that the modulus are equal. So I guess there hasn't been any enlargement, as we said before. And to plot them on an eigendiagram, I'll try and fit it in the small space. I probably don't need the bottom half, I'll just make it low. Okay, Z first, 1 plus I. So it must be 45 degrees that way. And then for WZ, it would have to be a rotation of pi on 3. This was meant to be at a 1:1 ratio because it was 1 plus I. So the angle over here must be 45 degrees, which means if we rotate it by pi on 3, it would have to go over the imaginary axis and be in the second quadrant. And I'll just indicate the angle in between. That has to be pi on 3. I think that would be good enough. Okay, so hopefully for the textbook exercise questions, there could be a few problems solving skills involved, but hopefully you guys would be able to do it. If you can't do it by yourself, work collaboratively, that's fine. Talk with the friends next to you and just have some group discussions if you get stuck on a question, or just send me emails. I forgot there was one more dot point. This video is getting long. I said we're going to talk about 2 things. The first one was the rotation and the enlargement together. The second one is shifting across the number plane. So, I should say complex number plane. Sometimes you might have 2 different points and you might be asked to find things about the interval that's joining those 2 points. In that case, we need to think about the difference of the coordinates between those 2 points. Now, this is going to make a lot more sense if we did vectors first, but because that chapter is going to be covered in term 1 of next year, hopefully when we revise the chapter it will make more sense. But we do start talking about vectors in the latter exercise in this chapter as well, so it's not too far away. Now, as an example, I've just got an example diagram where I've got point Z here, I've got point W here, and to make it easier, I've just put in random coordinates as an example. So if I've got Z as 10 plus 10i, and if I've got W as 6 plus 2i, then how would I represent the interval that's joining W and Z, so line WZ, using the coordinates form? If you've had a look at vectors before, you might have guessed it really easily, but what we could look at is, as the notes say, we look at the difference between the coordinates of them. So imagine subtracting away these coordinates from Z, as in Z minus W. Well, W is pretty much saying that from the origin it went 6 to the right and 2 up. So to subtract that whole complex number from Z, we are going to go down by 2 and 6 to the left. And that's where we get. So then if I try and join the origin and the final place that we got to, that interval is the exact same interval that is joining points W and Z. I don't know if you saw that transition on the video. I don't know if it's recorded. But yeah, that's why we look at the difference between the coordinates. So if you wanted to find the length of the interval joining W and Z, you just have to look at the modulus of Z minus W. And if you wanted to find the angle alpha, which I haven't indicated on the diagram, I might just get rid of the example coordinates to show more clearly. When I say the angle alpha, what I mean is, and what most of the questions would mean, is that they're looking for the angle between the horizontal and that line interval. So this would be the angle alpha that they want you to find. And if we have to find that angle, we would have to also look at the argument of Z minus W. So keeping that in mind, let's try the last example. Okay, example 24. Let points W and Z represent da-da-da-da-da, and we're going to find the length of interval WZ and the angle theta that the interval makes with the positive x-axis. So let's have a look. I would like to picture that first. So, oh, that's not the color I want, but that's okay. Okay, W is 2 plus 2i, right there. And then minus 1 plus 5i, that's pretty high up. That would be the point for complex number Z. If we have to find the length of WZ, then we are going to have to look at this length, which, as we said before, the length of WZ would be the modulus of Z minus W. And if you subtract the coordinates, you can see that it's going to be -3 plus 3i. And it's really easy to find that length. Just the square root of the sum of the squares. Or, as I said before, if you can sort of figure out that this is going to be an isosceles triangle, you can use the exact value ratios. That was part A. Part B. To find the angle, again, we look at the argument of the difference of those two complex numbers. So that would be argument of -3 plus 3i. If you picture that, it would have to be in the second quadrant. And again, it's isosceles, so we already know it's going to be pi on 4. So the principal argument would be 3 pi on 4. And that is it. It was a long video today, and as I've covered a fair bit of things, the homework list is also pretty long. I'm very sorry about that, but try and get as many questions as you can get done. And if you really don't think you can get most of it done, at least trying to get the easy ones done first, and then you can come back to the harder ones later on when you're revising for the chapter. So I've already put a task on Connect, so if you're done with these 4 exercises, you can tick them off. Again, if you have any questions, let me know via email. Good luck!